Hello there. In this video, I kind of want to make a part 2 of the rationalizing the denominator. I also want to talk a little bit more about what I talked about in our dividing complex numbers video, where I talked about rationalizing by using a conjugate. Okay. I want to do it with radicals again, so it's like a rationalizing the denominator with radicals part 2. But I also wanted to take a time to discuss the property. This came up in a couple videos. The square root of a times square root of b equals the square root of a times b. We learned in the multiplying binomial radicals video that this is only true if a and b are both greater than 0. Okay, so, and you can go back and watch that video if you need further clarification. Make sure you skip to the end because that's where the explanation is. But this leaves us a question. What about the square root of a divided by the square root of b? Can we split this into the square root of a divided by square root of b? And the answer is yes, once again, if a and b are greater than 0. Well, actually, and a could be equal to 0 in this case. I suppose a and b could be equal to 0 in this case as well. They just can't be. So let's go ahead and correct the record on that and make that negative. So a, if I wanted to be specific, greater than or equal to 0, and b has to be just greater than 0 because, again, we can't divide by 0. So I wanted to bring this concept into my videos because I do want to make sure I can address it in the future. So in simplifying this first term, I can turn this into the square root of 4 over the square root of 9. They're both positive integers. And it doesn't need to be an integer, but positive nonetheless. And that gives us 2/3. And that leads me to another thing I wanted to address. I think I said in a previous video that if you have a square root of a non-perfect square, it's automatically going to be irrational. And I think I misspoke because it can be rational so long as the quotient, like this one that you are dividing by, are both made out of perfect squares, okay? Otherwise, anything is rational. So to sum that up, if it's a square root of a perfect square, it'll be an integer. If it's a square root of a ratio of perfect squares, it will be a rational number, okay? If it's a square root of almost anything else, so if there's some kind of non-perfect square thrown in there, then it will be irrational. And this just fits back to the definition of what an irrational number is. So I appreciate you bearing with me on that. Let's get on to the next example. So again, as I mentioned before, this is a video that's kind of like part 2 to the rationalizing the denominators with radicals. So I'm going to rationalize this by multiplying both top and bottom by the square root of 3. But note on the top, I have to distribute it to each term because there's this plus sign in the middle. So 21 times 3, well, that's just 63. And plus 12 times 3 is 36. Now, usually when it was multiplying binomials with the radicals, I said make sure you simplify first. I didn't happen to do that in this case. I probably should have, but it actually works out nicely. And then square root of 3 times square root of 3 is just 3. Okay. Well, square root of 36 nicely simplifies to 6. Let's get a factor tree for 63. That's 9 and 7, 3 and 3. And we get 3 root 7. And then, again, the square root of 36 is 6 all over 3. And we can actually take it a step further. Okay? Notice that 6 is 3 times 2, so we have a factor of 3 that we can factor out all around, and in the end we can just get square root of 7 plus 2. Now let's go ahead and use the properties of radicals to solve this in another way. So I'm going to go ahead, let's try that simplification process. So square root of 21, that doesn't simplify other than to say that 21 is just 7 and 3, but I'll show you what. If I get a 3 there, then I can note that I can do square root of 7 times square root of 3. Again, they're both positive numbers, so I can separate them. And then 12, from past videos, I know to be 2 square root of 3. And now I don't even need to mess around with the algorithm of rationalizing a denominator, because like I canceled out that 3, I can also cancel out these square root of 3's, and I'm left with 1 in the denominator. So my final answer is square root of 7 plus 2. I don't like that. Let me fix that really quickly. All right. And that's our final answer. So again, you can choose which method you like better. The other method works best 100% of the time. This method truly only works when you can spot those patterns in the numbers. So let's talk about one more example. Let's talk about this because this relates back to multiplying by the conjugate of the denominator in my complex numbers video, dividing complex numbers video. So I'm going to do the same thing here. The only way to rationalize this denominator and to simplify this problem is to multiply the bottom by square root of 7 minus the square root of 5. Okay? I will do the same to the top. Square root of 7 minus the square root of 5. Okay? Now, there are shortcut formulas that I will be going over in future videos that I'm not going to go over in this video. So for now, I'll stick with the area models. And we'll talk about those formulas in the future. If you really want to see those quickly, go ahead and leave a comment in the comment section. Okay, so we got 7 square root of 7, negative square root of 5. And then this is for the numerator, so it's basically the same thing. Square root of 7, negative square root of 5. 7 times 7 is 49. I know the square root of 49 to be 7. I get negative square root of 35 here. I get 5 times 7, so that's another negative square root of 35. All right. And then I get 5 times 5 is 25. Square root of 25 is 5, but I also have the negative times the negative, so this is 5. And I can see that this diagonal adds up. And I've got 2 of these. Those are simplified terms, so this is negative 2 root 35. So I'm going into the margins on this one, but that's okay. So this is 12 minus 2 root 35. And then we'll go ahead and I'll do it in a different color. So we got square root of 7, square root of 5. And then I got square root of 7, negative square root of 5. Okay. And again, I get square root of 7 times square root of 7. That's just 7. I get square root of 5 times square root of 5, or negative square root of 5 times square root of 5. That's just gives me negative 5. And I get negative root 35 here and root 35 here. And remember, this creates the property that when we're multiplying by the conjugate, this diagonal should cancel out. Okay, and we just get 7 minus 5, that's over 2. And notice we have a 2. We can cancel out of all of these. So our final answer is just 6 minus root 35. Go ahead and leave a like and subscribe. If you want to see any particular videos in the future, leave a comment in the comment section. Thanks for watching.